Alright, the simulation tools let us specify a description of what we want inside each cell, what functions we want each cell to perform, and we do that in a plain text file. That file is compiled using some of these tools and then loaded into the simulator as a binary image, and the simulator goes ahead and mimics the behavior of the songline processor. And there's a couple of different varieties of simulation. There's software simulators, which simply put up a graphical interface and let you change the inputs using sliders and look at the outputs on some bar displays. But there's also one version of a physical songline processor, and in this version we have 4 input channels we can control with these knobs, and we have 6 output channels, and we can choose which one we want to look at and see the output voltage on a meter. And there's also connections we can make on the back to external input and output sources, and those will be available for display through whatever we hook up to this. This whole thing talks to a computer through a USB port, and the computer runs the actual simulation engine. This is really just the I/O unit. So we'll play with this in another video, but let me show you how we might write the code for this particular circuit to implement a D flip-flop. So the code looks a lot like C because we actually punt to the C compiler to do some pre-compilation of this code. So here's how we could define this circuit. We use a command called setTT. And setTT does the following. We give it a row, a column, an output, and an input. So let's set up this cell's truth table. So we would say something like setTT, and this is row 1, column 0, and we want to set the K output, and in this case we just want it to be equal to whatever value is coming in on the left, and that's just L-val. And that specifies this cell's behavior. This cell up here, we need a pair of equations. Set TT, so this is row 0, column 1, 0, 1, and we're going to set its left output to be whatever value is coming in on the left. And set TT 0, 1, and we want its K value to also be whatever is coming in on the left. So that mimics this piece of the wire. Now this cell's function is contingent. It's contingent on the value of K. And we have 64 bins, so our inputs are between 0 and 63. So we could actually write K is less than or equal to 32, or K is bigger than 32. And so we can write the following: if K is less than or equal to 32, set the TT of 0, 0, and we're setting its right output to be K is less than or equal to 32 to be just the R val, else set TT 0, 0, R to be the L value. And there's a program that describes our 3-cell songline circuit. Now, it's one of these things where if you don't think about it too deeply, it makes sense, right? This if-then-else statement is coding our intention here, which is if the K input is too small, then we set the truth table like this. If it's too large, we set the output like this. The fact that this if statement is changing the function that's going to be compiled in here can seem a little weird, because it's got a blurry distinction between runtime and compile time. That's not surprising. If you've studied the cell matrix, you know that that blurring of runtime compile time is sort of endemic in the whole cell matrix architecture. And I think that's what we're seeing here, is that this is code we're going to compile, but the code that's compiled as a result doesn't contain an if statement, right? The code that's compiled is such that we get this effective behavior. If K is less than 32, the stored function looks like this, otherwise it looks like this. don't think about it too much unless you like that kind of thing. So this is the code for a D flip-flop sample and hold circuit. There's also a configuration file that goes along with the compiled binary for this, and that configuration basically maps inputs and outputs to particular channels, so that if we're looking at the behavior of the circuit on something like this, we can say let's map the input to channel 0, map the load to channel 1, and now we can use this knob labeled 0 to control the input, this to control the load line, and we could say let's put the output on channel 1, and by putting this on channel 1 we can see the output on the meter. So we'll actually do that demo in a few videos, but let me talk about C-mode behavior next.